Hello everyone. Let's continue with our previous lesson, which was about how to convert the system, the binary system or the system of the numbers in the computer to hexadecimal or binary to hexadecimal or octal to hexadecimal. All of them. We have to convert all the numbers to binary or binary to the others, or vice versa. Our lesson today is going to be the same, like hexadecimal to binary. In this lesson, I'm going to show you how to convert the hexadecimal numbers to binary, as we see here, from hexadecimal to binary. We're going to convert them. I'm going to show you how you do the technique and how you get the result at the end. So the technique of the hexadecimal to binary, to convert it, we have to convert each hexadecimal digit to a 4-bit equivalent binary representation. So we have to convert the hexadecimal digit to a 4-bit equivalent binary representation. For example, we have to convert 10 AF in base 16, which means base hexadecimal, it shows here 16. You have to know always the base which is represented. This one represents the hexadecimal 16. We have to convert it to binary, which is 2. Binary is 2, like we is then in the base 2. So 10 AF in base 16 to which in base 2. First of all, we have to write the number from the right to the left, from the left to the right, which is here, 10 AF. Then we have to write we have to divide it into 4, as we see here. 4, 0, 0, 0, 1, 4 zeros, 1, 0, 1, 0, 1, 1, 1, 1. So under each one, we have to divide it into 4 bits of binary. And this one represents the ones in binary. This 0 represents the 2. This represents the 4th in the binary. So this one, 2 by 2, it's 4. Again, 4 by 2, it's 8. So in this one, it shows us that the number will be 1, because it's represented in the base 1. So this one will be 1. 0, there is no represented in 0, so will it be 0. A in hexadecimal, it means 10. So we have to convert 10, which is in hexadecimal, A, to binary now, which equal to 1010, which means 0 in base 1, which is 0, 1 in base 2 is 2, 2 multiplied by 2, it's 4, so 0 in here, and 4 multiplied by 1, 4 multiplied by 2, it's 8. So 8 plus 2, it's equal to 10. So 1, 0, 1, 0. Now we come to F. F, again, we do it the same. 1, we write like 1, 2, 4, 8. So 8 plus 4 is 12. 12 plus 2, it's 14. 14 plus 1, it's 15. So F in hexadecimal to binary, it means 15. So 10 AF in base 16, it shows us the result, this one. So we have to write it from the left to the right. So we write these from the left to the right. And we have to write in which base we convert these numbers. So we convert it from the hexadecimal to binary. So binary represent in base 2. So we have to write 2 at the end. Again, we have to write it from the left to the right, and we have to write the base. If you don't write the base, that means you just any number you write down. So in the exam, you will get 0. So you have to write for me in which base did you convert it, and the one I'm asking for. Now we're going to convert the decimal to octal. how we convert decimal to octal. It's very easy technique, and I'm going to show you this now. The technique is we have to divide it by 8, and we have to track the remainder. So we have to keep the remainder, and we have to divide it by 8. Let's convert, for example, this number 1, 2, 3, 4 in base 10, which is decimal, to octal. Octal, it's base 8. 1, 2, 3, 4 in base 10 to 8. 1, 3, 4, 1, 2, 3, 4 divided by 8, it's 154. And the remainder is 2. So we divide this number by 8, we get this result, but the remainder, as I said before, we have to keep the remainder, so which is 2 in here. Again, we divide 154 to the base 8, and the result will be 19. But the remainder, we have to keep it as well, which is 2 in here as well. Then we divide 19 again by 8, which is 2, and the remainder is 3. So we keep the remainder as well for each step that we divide. 2 divided by 8, which is 0, but the remainder is 2. So we keep this as well. And then we write it from the bottom to the top. We write the remainder to show us the result here. So we write 2, 3, 2, 2 in base 8. This is how we convert decimal, which is base 10, to octal in base 8. So 1, 2, 3, 4 divided by 8. Again, I'm going to say it to you, show it to you. 1, 2, 3, 4 divided by 8. It's 154, but the remainder is 2. Again, 154, we divide it by 8, we get 19, but the remainder is 2. We keep the remainder. 19 divided by 8, which is 2, but the remainder is 3. 2 divided by 8, which is 0, and the remainder is 2. We write it from the bottom to the top. So from the bottom to the top, which is shows here 2, 3, 2, 2 in base 8. In base 8, which is octal, as we see here. Next step, we're going to show you now how to convert decimal to hexadecimal. This technique is very easy as well. The technique will be divided by 16, and we keep the remainder. So it's the same thing with the octal, but we divide it by 16. The octal we divided by 8, which is the base of the system. Now we divide the hexadecimal to the base 16. Again, the same example in 1, 2, 3, 4 in base 10 to the base 16. How we do this technique, I'm going to show you how we solve it. 1, 2, 3, 4 divided by 16, it's 77. The remainder is 2. 77 divided by 16, it's 4. We keep the remainder, which is 13, and it's equal to D as well. 4 divided by 16 is 0, and the remainder is 4. The result is 4D, which is D is 13, as we said, and 2 in base 16. So that was like the same thing with the octal, from decimal to octal, but now it's like same technique, but different system. In base 10 to 16, we divided by 16. From base 10 to 8, same thing. We divide by the same base, and we keep the track of the remainder. 4D, 2 in base 16. Now we're going to convert from binary to octal. We will see how we're going to do it now, but again, it's going to be easy for you. The technique, we group bits in threes. So each group, we're going to be like a group it in threes, starting on the right. And then we convert the octal to octal digits. We're going to convert this number 1, 0, 1, 1, 0, 1, 0, 1, 1, 1 in base 2, which is binary, to what this number represent in base 8. So we're going to convert this number to the base 8. So we write it like this from here, 1, we separate it into groups of threes, 0, 1, 1, 0, 1, 0, and the last thing we divide this, we write this like three groups, 1, 1, 1. So 1, it's equal to 1. This is equal in binary to 3, and these are equal to 2. 1, 1, 1, it's equal to 7, which is, I'm going to show you what. 4 plus 2 is 6, plus 1 is 7. Here is 1, 2, and 4. So this one is represent the 2's, so we write it 2. This one, 1's plus 2 is 3, and we write 1. So the result will be, again, 1, 3, 2, 7 from the left to the right, and we write the base, which is base 8, as we see here. Now we're going to convert from binary to hexadecimal. The technique is group bits in 4, starting on the right. Second thing, we convert to the hexadecimal digit. So we're going to convert again 1, 0, 1, 0, triple ones, 0, 1, 1 in base 2 to base 16. Again, we said we group is in groups of 4, as we see here. We take 1, 2, 3, 4. We put it here. Again, we take this number 1, 1, 0, 1. We group it here, and we take 0, 1. So it doesn't matter. You can write 0, 0 at the end here. It doesn't matter. Any number, any 0 on the left, it doesn't mean anything. So we can write 0, 0 if you want to make it in group of 4s. Again, now here, we say this one represent the 1s, 2s, 4s, and 8. So 8 plus 2, it's 10. 10 plus 1, it's 11, which equal to B in hexadecimal. Here again, 1s, 2s, 4, and 8. 8 plus 2, it's 10, plus 1, it's 11. It's equal to B in hexadecimal. And we take the 2's because this one represents the 2's. This one represents the 1's. This one represents the 2's. So we just write 2. So the result will be 2PB in base 16. So this is how you convert 2's, the binary, to 16, which is the hexadecimal. It's easy, very easy step. You just group it in bits of 4s, and you get the results. Now we're going to convert octal to hexadecimal. The technique is use binary as intermediary. So base 8 to base 16. We're going to convert 1076 in base 8 to the base 16, as we see here. So we write it from from the left to the right, 1076 in group of 4s. So 6, let's say 0, and represent the 1s, 1 represent the 2s, and this one represent the 4th. So 4 plus 2 is 6, which is equal to 6. 1 plus 2, 3. 3 plus 4 is 7. This one shows us 0 because it's 0, and this one 1. So the result will be 2, 3E. 2, 3E in base 16. So 2, 3E in base 16. As we see here, 1076 in base 8. The result will be 2, 3E in base 16. Now we're going to convert hexadecimal to octal. How you convert hexadecimal to octal? Very easy step as well. We use the binary as the same thing with the last one we did. 1F0C in base 16 to the base 8. We're going to convert this number in base 16 to the base 8. We write it from the left again to the right. There are many techniques to do these things, but I'm going to show you only the easy techniques. There is very hard techniques to do it, like divided or doing many things. But this one is the very easy one. Again, C, we divide it to 4. So C, 0, 0, 1 1. This one will show us 40. F, which is 15, which is 8 plus 4 plus 2 plus 1, which is equal to 15. 1, it's equal to 1 in here. This doesn't mean anything because it's 0, equal to 0. So it will be 1 7 4 1 4. So we divide it into groups of 3s. So this one equal to 4, we write 4. This one is equal to 1. We divide it again, like we group it into base of 3. This one is equal 4. This one is equal 7. This one is equal 1. So the result will be 17414 in base 8. So base 8, 16 to base 8. So we divide it, we group it in 3 bits, and we get the result as here from the left to the right. This exercise will show us how to convert the decimal to binary, to octal, to hexadecimal. So we're going to convert 33 in decimal to binary, to octal, and to the hexadecimal. Again, we're going to convert 110101 in binary to decimal, to octal, and to hexadecimal. We're going to convert 703 in octal to binary, decimal, and to hexadecimal. We're going to convert this hexadecimal number, which is 1AF, to octal, binary, and to decimal. In the exam, in the final exam, you are not allowed to use the calculator or your phone. So you have to study for the final very well to do this calculation. So the answer will be as follows. We convert 33 to the binary, which is 1000001, octal, 33 in octal, which is 41, to the hexadecimal 21. This number in the binary, it shows us the result here 117 in the decimal, 165 in the octal, and 75 in the hexadecimal. 703 in octal, it shows us 1C3 in hexadecimal. This number in binary, 451 in the decimal. 1AF in octal, which is shows here 657 in the binary, 11010111, and in the decimal 431. So just this table, it shows us the result of how you convert the numbers between decimal to binary, binary to octal, and the hexadecimal without showing the step. So by doing the step, or the way I showed you to convert the binary to decimal, or decimal to hexadecimal, or etc., or like octal to decimal, it shows us the techniques that I gave you, and you will get the result for each number that I gave in the exam, in the exercise. So common powers in base 10, power 10, like base 10 to the power minus 12, which is pico, and the sample will be p. Base 10 minus 9, which is nano, we sample it as n. Base 10 to the power minus 6, which is micro, we call it, the sample will be m, like this, micro, which is m. 10 minus 3, which is milli, and the sample will be m, and etc., as we see here. To the last one, it's base 10 to the power 12, which is tera, and we sample it as t. Giga, we sample it as g. Mega, m. Kilo, it's k. Milli, it's m. So we have to know this table. If you use it in the future, maybe your major is not computer, or not, you're not into computer, but you have to keep it in your mind. One day you will use it. The value in each power is this value, as we see here. Again, the value will be the base 2 in power 10, which is 124. Base 2 in power 20, this number. Base 2 in power 30, which is giga, which shows us this number. If you go to your computer, my computer, and the desktop, and you do like right click, and you go to properties, you will find how the capacity of your computer in bytes. As we see in this computer, not this computer, but the one I did, this number in bytes, which is 35 gigabytes. So it shows you exactly and shows you how the free used space and free space. This is how you get to the, as we see here, 1977 475.072 bytes, which is equal to 184 gigabytes. So which is equal to 2 in power 30, this number. This exercise determines the free space and all the drives and the machine in the lab. So this one we don't have to do it, but I'm going to show you. For common A, B time A, C, it's equal to A to the power B plus C, and which gives us like example, or we do it like this one. And we have to write which is equal in what? In kilo, in gigabyte, tera, etc. or mega. Binary addition. A plus B, which is 0 plus 0, which is equal to 0. 0 plus 1, which is plus 1, shows us 1. 1 plus 1 equal to 1. 1 plus 1, it's not 10, it's 1, 0. We write it as 1, 0 as binary. So because it's binary, we don't read it 10, we read it 1, 0. So 0 plus 0 equal to 0. 0 plus 1, 1. 1 plus 0 equal to 1. 1 plus 1, it's equal to 1, 0. And base 2, which is binary, as I said. It's enough for here today to finish with this lesson. Next lesson will be about communication network, and we're gonna talk how did it start, when did it start, how do we use it, what does it mean, www, etc. So next lesson will be about network and communication. Thank you very much for today. See you for the next week.